Okay, here we go. Just about made it. Right, I've been outside all day, so I feel a little bit unprepared, but I think we'll probably be fine. Picking up from where we were yesterday. So, right, okay, let me get it together. Right, so yesterday we started to think about how to install software. That was the goal for this week. Is to build ourselves a script which can download some data and build us a multiple alignment from the protein sequences that we download. So in order to do that, we needed some software that enables us to build that multiple alignment. And that's what we spent yesterday doing. So yesterday we installed Conda, which is a software management and software environment management system. And as I said yesterday, it was originally built for managing people's Python environments, and has kind of expanded from there to manage software more generally. So yesterday we installed Conda, and then right at the end, in somewhat of a rush, we set up an environment and we installed Muscle, which is our multiple sequence aligner, into that environment. So that was, I accept, I spent a lot of time kind of in the setup yesterday and not very much time in the execution at the very end. So I thought I would just, at the very beginning here today, just kind of repeat those steps that we had at the end yesterday to get our software installed in an environment that we can use. So if we just flip over to my whiteboard, there we are. So because of the aforementioned all day spent outdoors, we haven't had time to do a picture of the day today. Maybe I'll show you a picture of the pond that I've built. If I can drag one onto my computer, right? But for now, let's just clean this up a little bit, and then I'll write some things down. Okay, so that okay, so this URL is the place that we download Conda from. So this is where we downloaded the software from that's going to manage all the rest of our software. That's our that's our installation of Conda. We got it from that URL. So we use wget to download that because we're familiar with wget now at the command line, and that worked very well. We also checked, if you remember, we checked the hash. It was a SHA-256 hash, and we checked the hash of the file that we downloaded using the program SHA-256-SUM against the hash that is written against the download on the website, just to make sure that the thing that we've downloaded is the same as the thing that they're distributing, that we haven't had somebody in the middle or between Anaconda and us feeding us something which isn't the mini Conda installation script, because that's a script that we're then gonna execute in our system, and because of that, we just wanted to make sure that it definitely is the thing that we think it is. We don't want to arbitrarily run code from the internet. That's not terribly good practice. So then once we downloaded that, we invoked it using bash. So actually using the executable, which is our shell. So this is the shell that runs all of our programs, but in this case we're explicitly invoking it to run this mini Conda installation script that we have downloaded from the internet, latest Linux. That's an x86 64, so that's the 64-bit version .sh. I think somebody commented that They couldn't get the 64-bit version to work, even though their VM was 64-bit. So they downloaded the 32-bit version instead. In theory, that won't have huge effects. It will just be that Miniconda will install the 32-bit version of all the software rather than the 64-bit version. The problem will come is if any of the software that we're trying to download is distributed only as a 64-bit version and not as a 32-bit version. Maybe we can check that for some stuff later on. But otherwise, it might be worth investing some time and energy to try and get the 64-bit version installed. But otherwise, if everything is distributed as both 32-bit and 64-bit, then actually it shouldn't really matter too much. So that was the installation process. And then what I talked about was two things. I talked about environments. So these are these two concepts from Conda, environments and channels. So environments, we can have lots of them. By default, we have an environment called base, and that's the environment that Conda creates for us when we install it. So that's our default environment. But we also can create new environments, and we can create new environments with the command conda create, and then -n and a name for our environment. So that will create an empty environment for us to start installing software into. Okay, so you can install software into your base environment. There's nothing necessarily wrong with installing software into your base environment if you just want to install everything in one place and you're pretty sure that you're not going to need different versions of particular software and things like that. Then you can install everything into base. That's fine. But if you ever think that you're going to need more than one version of a particular piece of software, or you want to keep your software installations for different projects discrete, then it makes sense to have separate environments for your different projects. So in this case, we created an environment called MSA for installing our software into. So that's the environment that we've created for our multiple sequence alignment project that we're undertaking at the moment. And once you've created an environment, in order to work in that environment, you need to activate it. So you need to type conda activate MSA, which is the name of our environment, and that will activate your newly created environment. And the text in your terminal prompt will change from saying base in brackets on the left hand side to saying MSA in brackets on the left hand side, and that's the cue to you that shows you that you have activated your environment correctly and you're now working in the right environment. So that's environments. The other thing that we talked about briefly yesterday was channels, and channels are the places where Conda gets software, downloads software from to install on your system. So when you install Conda, Conda only knows about a channel called defaults. So this is the Anaconda repository of software that can be installed by Conda and is managed by Conda, and it's got 700 or 800 packages. It's got quite a good range of software, but it's not necessarily got everything that we want, and it doesn't necessarily have the most up-to-date versions of everything that we want. So we added a couple of extra environments to make sure that we can get everything that we need for our projects, and those two environments that we added were Condor Forge, which is a place where kind of generic software is made available, but is generally, so it's user contributed, so it's maintained by the community, and it's generally kept more up to date than defaults is, and has a wider range of things. Tends to have kind of hundreds more packages available at Condor Forge. And then the other channel that we added to make sure that we can install all of the software that we want was Conda. And Conda is a channel for bioinformatics software. So that was the channel that we added to make our bioinformatics software available to us. So that was a really that's going to be a really helpful thing to us going forward, to make sure that we have that channel available. Okay, so if we go just nip to our VM and then clear my screen. So I'm going to exit my terminal and launch a new one. So click on the mouse, click on Terminal Emulator, and then maximize. So when you start a new session, so I've logged out by typing exit, and then I've logged back in by reopening a terminal. So this has started a new terminal session, and it's dropped me into my base environment. So by default, you will always open up in your base environment when you start a new session. So we've logged out, we've logged back in, and I'm in my base environment. Okay, so that's fine. I'd like a way of checking my channels, and I don't know what the command is for that. Let's see if we can find out. Here we are. So here's all of the, so Conda, there's other commands that are like this that we'll come across as we proceed over the next few weeks. Conda, the command is not like any of the programs that we've run so far, where you write the command and then you write your arguments. Conda does require arguments, but it requires a named argument, which is essentially a verb. It's the thing that you want Conda to do. It's the thing, the action that you want Conda to take. And so here's a list of commands for Conda that we can give it. So config, which is what we used to add our we used config to add our new channels yesterday. So we ran Conda config, and then we added some new channels. And then there's a bunch of other things as well. We can list our packages. We can install new packages. So install is an action that we can take. We can search. We can update our existing installed packages if we want. So if we run a Conda list, that will list all of the packages that are installed. This is in my base environment. Okay. So this isn't this doesn't include my MSA environment. So you will find that the muscle package that we installed yesterday, our multiple sequence aligner, is not in this list because that's not installed in our current environment. And we'll activate the MSA environment in a second. We can type Conda info and see what information that gives us. There we go, and that's telling us the channels that we've set up. So in our info, it's telling us where we've installed, what our active environment is, where we've installed to, where our config file is, what version of Conda it is that we're running, what Python version, and what channel URLs we're querying when we make a query, when we try to install a package. It looks in these various places for the packages that we want to install. So, and because we added our channels in a particular order, and that order is reflected here. So the first place that Conda will go and look for a new package is in Condor Forge. So it will go and look in Condor Forge under our Linux 64, so that's our 64-bit architecture, first of all, and then in no architecture, so for things which it will have to compile from source. And then it looks in Bioconda, and then it looks in the default repositories. And then this is the places where those packages get installed to. Okay, so I'm going to activate my MSA environment. So Conda activate MSA. Okay, so that will switch on the right environment. There we go. So the text at the beginning of my command prompt has changed. So instead of saying base, it now says MSA, and that's because I've now activated my MSA environment. And now if I write conda list, we'll get a slightly different list of packages, a shorter list, because we set this environment up with not very much software. And included in that list of packages is muscle. That's our multiple sequence aligner that we installed yesterday. And alongside the packages which come from not from the defaults repository but from somewhere else is the channel that software package has been installed from. So we can see muscle has been installed from Conda, and there's a few other things which have been installed from Condor Forge, which were dependencies of muscle, and that's where they were found. That's our MSA environment, and in there we have all of the software that we need for the job that we want to undertake today, which is we're gonna look at our script that we wrote the other day, and we're gonna modify it so that we can use this muscle multiple sequence alignment program that we downloaded with Conda, installed with Conda, to align our 12 ACE protein sequences to each other in a multiple sequence alignment. So that's our task for today. Okay, so we're in the right environment. We've got the software installed that we need. So now we're going to run we're going to modify our script we're going to download the data again because we want our script to be self-contained. And then we're going to use muscle to construct our multiple sequence alignment. Okay, so that's our task for the rest of today. So the first thing that we're going to do is we're going to change our working directory. Because I logged out and logged back in, I am currently, my current working directory is my home directory. So I'm going to change directory into my week 3 directory. So I'm going to cd into share week 3. There we go. We're going to list to see what we've got. So we've got all of our FastA sequences that we've already downloaded. And what I'm going to do actually is I'm going to remove those because I don't want wget to get confused by the fact that we've already got the files that we're downloading in our current working directory, because it will re-download them, but it won't. But wget by default will refuse to overwrite those files, which is fine. It doesn't really matter too much. But we'll end up with all of those sequences again, just with it will be the file name with a .1 on the end. Because wget will re-download them, we'll have twice the amount of data, which for these little protein sequences doesn't matter too much. But if we were downloading more substantial data, which we will be in the future, it really would matter if you start to download everything twice. So I'm going to rm star.fasta, and that will delete all of those FastA sequence files that we downloaded on Monday. We need to bear in mind that this is an RM, and when we do RM, we don't get asked for confirmation. We don't get asked whether we're sure. Things don't get moved to a recycle bin; they just get deleted from the disk, which very quickly makes them impossible to recover. So we're going to RM here. We need to be sure, especially as we're including a wildcard. So we've got a star in our command, that this is definitely going to do the thing that we want it to do. One way to check would be rather than running RM first, run ls. To check that your wildcard is doing the thing that you think it should be doing. And then ls will tell us that we're definitely our wildcard is just matching us our FASTA files and not lots and lots of things. I'm just going to jump in on the thing in the comments at the moment. Condor Forge has a hyphen in it, so it's Condor-Forge, which is why you won't find it. There you go, somebody's come up with the same thing. I'd like to think that I'm not completely ignoring the comments, although they do kind of go past in a blur most times, because I'm still not terribly experienced at this whole live streaming thing. Okay, so the ls that I've done here is confirming to me that my wildcard is definitely only matching the files that I want to match, and so I'm going to change my ls back to an rm, and that will remove those FASTA files from my present working directory. So those files have now gone, and just to confirm that with an ls, you can see that I still have my scripts and my UniProt IDs file, but I no longer have my FASTA sequence files, and I think that's probably a good place to begin. So we're going to edit our script, get UniProt data. And we're going to edit it so that we can download those sequence files and get the data that we download into a format that Muscle requires. And then we're going to run Muscle outside of our loop. So we've got a for loop in our script. Outside of the loop, once the download is finished, we're going to run Muscle to construct the alignment. So before I start editing the script, I'm going to look at Muscle's help information. So Muscle won't have a man page because we've installed, it's not a Linux system tool. We've not installed it with apt, we've installed it with Conda. So if we type man Muscle, we won't get a man page because it doesn't have one, because Conda doesn't install manual pages for us. So instead, I'm going to run Muscle with no arguments, and this will usually return me an error. It will tell me that it can't run, but it should also either give me the help or tell me how to get to the help. And a command that's been written in a reasonable fashion should let you get to its own help page relatively easily. So one of the first things that you would do with a new command is just run it with no arguments, and that will usually get you to some sort of help or some instructions for how to get to the help. So there you go, Muscle has actually printed out a little bit of help information for us. It doesn't tell us how to get to anything more detailed than this, but this is probably enough information. So we've got the basic usage up at the top here. So Muscle, -in, and then an input file, and then -out, and then an output file. So that's relatively straightforward. Here we go. We'll take a note of that. So let's go to our whiteboard, whatever this is. Goodbye, Disco Chick. We'll take a note of it up here. Where's my pen? There it is. Okay, so what was it? Muscle, in file, out file. Straightforward enough. Okay, so that's that. In input file, out output file. We've got some other settings here. Let's read about the input file. Okay, so in is an input file in FASTA format. Okay, default standard in, but we're going to want a file because we want to keep our input file on the disk. So it's not saying multiple files. So we're downloading 12 FASTA files in our script, but Muscle just wants a single file. So we need to be able to do that. In our script, we need to be able to take our files that we've downloaded, and we need to construct a single input file from those 12 files that we've downloaded. Okay, so that's one task that we need our script to be able to accomplish. Okay, the output alignment, so -out, will come out in FASTA format. I think as a default, I think that's fine. The FASTA alignment format isn't terribly understandable, but it's good enough for us for a first look. If you want a more sort of human readable format, the Clustal format is probably slightly more readable. So maybe we'll add this CLW argument to get the Clustal output from our alignment. So let's take a note of that as well. Okay, so dash CLW is the other argument that we want to add to our command. Okay, so other than that, I don't want to mess too much with the kind of default operation of muscle at this point. We're not necessarily in this today to try and understand multiple sequence alignment. We could always spend another hour on that another time if people really wanted to. But today we're just wanting to produce a multiple alignment, and we're going to make the radical assumption that the defaults for muscle are fine, which is admittedly, taking a reasonable chance with our putting a lot of trust in the developer of muscle. But I think it should produce an okay alignment. Right. Okay. So that's everything we need to know about the operation of muscle at this point. That's what we need to know. What we know from that, what we need to do is to be able to take our 12 FASTA files that we download from Uniprot, and we need to use those 12 files to construct a single input file for input to muscle. And that's our big take-home message from reading this help file. Okay, so let's go into our script and let's start editing. So nano, and then the name of the script, which is get uniprot data.sh. Okay, so here is the script that we wrote earlier in the week. I think we wrote this on Monday, didn't we? I'm just going to add a couple of additional comments. So here we go. So get input data uniprot IDs. Okay, so I'm just making a note for myself as to what this line here is doing. This is a loop for downloading the data. Okay, so how do we need to change this? So at the moment, what this is going to do is it's going to go and download from the Uniprot website via their nice API that they provide us for downloading data. This is going to go and download the FASTA sequence for all of the Uniprot identifiers that are in our input file, that are in our uniprotids.txt file. So that's what this does at the moment. We know that's what it does because we used it to do that on Monday. What we want to change, therefore, is we want to, after we've done the loop, we want to run muscle. So we're going to run muscle down here. Middle click, run muscle to build multiple sequence alignment. So here we are here we're downloading Uniprot entry. And then what we want to do is we want to use our Uniprot entries to build a single input file for muscle. So we want one file to give to muscle, which contains all of our sequences. And I'm going to do this by within the loop by using some of the things that we learnt about back in the first week. So we know that the tool cat will print out the contents of a file to standard output. Okay, so we've got a file now in our present working directory called whatever the Uniprot identifier is this round of the loop. So $i.fastA. Okay, so that's the file that we've just 2 lines above downloaded from Uniprot. I'm just going to put another comment in. I'm just trying to be a good citizen about my comments. Construct muscle input. Okay, so cat will print the contents of that file to standard output. That's not terribly useful to us. What is useful to us is the fact that we can redirect that output into a new file. So we can use the greater than symbol to redirect the contents, whatever cat is going to print to standard output, into a file. So we can create a file here called muscle input.fastA, because it's a fastA file. Okay, so this is using cat to redirect the contents of a file into a new file. And at this point, all this is doing is making a copy of that file, which is not a terribly useful thing to do. But if instead of using a single greater than symbol, a single redirection symbol, if instead we use 2, so here we go, put a second one in there, what that means is not just redirect this to this file and overwrite whatever was in that file before. So what that would have done is each iteration of the loop, it would have overwritten what was in that file. So it just would have been, the contents of that file would have just been the Uniprot entry that we downloaded most recently. Instead of that, what this now does is it appends to the end of that file. So the first iteration of the loop, the file doesn't exist. So this redirection operation creates it and puts into it the contents of the first fastA sequence file that we've downloaded. What happens in the second iteration of the loop is the second Uniprot entry is downloaded, and this time, instead of this file being created or overwritten, I'm just watching a red kite fly by my window, which is excellent. Sorry, got distracted. Instead of overwriting the contents of the file, which was the first Uniprot entry with the second Uniprot entry, what this does now is appends to it. So it adds the next entry onto the bottom of the file. And then the third time round, it adds the third entry onto the bottom of the file, and so on and so on. So every time this loop goes round, that file gets a bit bigger. And that's exactly what we want to happen. That is the input that we then need for muscle. Okay, so that's exactly what we want for our multiple sequence aligner. And then, because we're effectively taking a copy of all of that data, because we're effectively copying each file as we download it into our muscle input file, we can actually remove the file that we've downloaded from Uniprot, because we don't need it anymore. So we can rm $i.fastA, and it's good to tidy up behind ourselves, because if we've got a copy of it in our muscle input file, we don't need to keep it. We don't need an additional copy of it it's wasteful. It's a waste of disk space, and we don't want to be wasteful with our disk space. It's not a good habit to get into. So we don't want 2 copies of each one of these files. We just want one in our muscle input file. Okay, so what I'm going to do at this point is I'm going to run this script as it currently stands. So I'm not going to add the muscle command at this point to this script. I'm going to comment out the muscle line down here like that. And I'm just going to run this script to check that it downloads the data in the way that we want it to download, to make sure that we get the data downloaded and into the format that we need it before we try and run muscle. So at this point, I'm going to save my script. So Control O to save my script. Press Enter to keep it in the same file name, which for now is fine. And then Control X to exit Nano. Okay, and then we're going to run that script. So my script is already executable. Let's just check. LH, just check that it's executable. Remember, in my share folder, all of my files are executable, and they're all executable by the group. My script is ready to go. The other thing to note, this script is getting relatively large now. We've done quite a lot in it already, and so we're starting to build up a respectably sized file. 448 bytes doesn't sound like a lot, but we'll be writing scripts that get a lot bigger than this as time goes along. Okay, so now we're going to run this. So to run it, we point bash at where it lives, so // and then get _uniprot_data. Okay, so now it's going to go and grab our 12 uniprot entries. It's going to cat them into a single file, and it's going to remove the original entries as it goes, to make sure that we keep tidy up behind ourselves. So off we go. So that's wget running 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and that's it. It's done. So our script has run. And now, if we ls, what we should find is we have just a single fasta file in in our present working directory, and no other fasta files. And that is indeed exactly what we've got. So we've got one fasta file, and none that are named after the uniprot entries. They've all been removed as our loop has gone around. And now if we ls lh to get a long listing format, we can see how big that one file is. And you can see that one script downloaded 11K of data. So not a huge amount, but nevertheless, that's a lot bigger. Each of the individual fasta files were all less than 1,000 amino acids, so they were all less than a kilobyte on the disk. So now we've got one 11 kilobyte file that contains all of our proteins, and we can just triple check that by using less to have a look. So less are our muscle input. There we go, muscle input.fasta. Again, using tab to tab complete so that I don't have to type the whole file name. This also avoids me making mistakes when I'm typing the names of files. So less to open it in a pager, and there we go. We can see that we have more than one fasta entry in this file. So we've got more than one greater than symbol in this file. And we can page through it to see that we've got lots and lots of entries here, and they're all protein sequences. The last one there is much shorter than all of the others. You can notice that straight away. So that last one that we've downloaded from some strange organism doesn't look very much like all of the others. And actually, that doesn't look to me like it might look like it's necessarily an ACE. So we'll see how that plays out in the multiple sequence alignment later. I may have mistranscribed an identifier there, because that doesn't necessarily look like an ACE or an angiotensin converting enzyme, as they are called. It's also not from the organism that I expected it to be from. So I may have mistranscribed an identifier there. We'll come back to that later. If it doesn't align very well, then maybe we'll have to modify our uniprot IDs script file at some point. Okay, so let's quit. So let's press Q to quit less. Let's also do one last check. grep for, now remember your single quotes here, you mustn't run this without the single quotes, for a greater than at the beginning of a line, and we want to count, so -c, muscle input.fasta. So this will count the FastA, the entries in our FastA file, because it's going to count the occurrences of lines that begin with the greater than symbol, which is the sequence delimiter for our FastA file. So that grep-c returns 12. So we know that there are 12 FastA entries in that file, which is exactly what we expected there to be. That is what we had anticipated. So that's a good thing. So that shows us that that we have the right number of sequences, the number that we expected to download. Incidentally, I am going to check that last identifier just now, just to make sure that I suspect I've probably got the wrong. I've probably transcribed the wrong identifier. So that last one, let's tail muscle input, is A0, A1, L8, E5, F5, which is indeed what I've got written down. Let me just have a look at something. Just getting everything off the screen here. Right, get rid of everything. Get rid of everything. Everything's, oh my goodness. Right, I'm revealing all of my dirty laundry. Sorry about that. Right, okay, so here we go. Let's have a look at, let's try and find the blast that I ran to identify these sequences. If I can find it. If I can't, I might have to come back to this tomorrow, because I suspect that that sequence is not going to align very well with all of the others, which is not the end of the world, but isn't necessarily the best thing ever. No, I don't think I can find it at the moment, so I'm going to have to look. Sorry, I'm kind of live debugging my own. Maybe it's in here. Hold on. One last place to look, and then I'll come back to it another day. No, it's not in here either. Right, okay, so I will look at this. I'll look at this between today and tomorrow and come back to it tomorrow. I'll check that identifier, make sure that we are actually downloading the right thing, because I'm pretty sure that that last sequence doesn't look like an ace to me, and it looks like it will probably mess a little bit with our alignment, although it's only one of 12, so it probably won't have too detrimental an effect. Right, okay, so that's me getting terribly distracted, and I apologise for that. Right now, then, I'm going to edit the script again to add in the actual running of muscle. Okay, so nano get uniprot data.sh. Right, so we know that the download bit works. Okay, so we know that this does exactly what we want it to do. We've checked that. I'm going to remove my muscle input.fasta before I rerun this, so that, because otherwise I'm just going to add the 12 sequences again to the end of it, and I'll end up with 24 sequences in it. That's we're gonna leave that bit alone, because we know that that bit works. So the next thing that we're going to do is we're going to actually we're going to work out our muscle command to actually produce our alignment. Okay, so down at the bottom here, we're going to run muscle. And if you remember, I'm just going to flip back to my blackboard. This is how we run muscle. Okay, muscle in file, out file, and we're also going to add this CLW option to get the clustal W out so the cluster W output format out. So we're going to put that in first. This is a good idea to have options in at the beginning. So -clw, and then in, and that's our input file, which is the file that we create in our loop. So muscle input dot fasta, and then our output, so -out, and our output is we can call it whatever we want. Right, it's going to be a cluster W format output file, but we can call it whatever we want. So we're going to call it muscle output.clw to tell us that it's a cluster file, that it's in that format. Because it's nice to keep our files named in such a way that that they make sense to us when we come back to them later. So this is just making sure that we know that this is an alignment file. Okay, so that's our muscle command. It's outside of the loop, so it's only going to run once the loop is finished. So once our loop has been round 12 times, our muscle command will run once at the very end. Okay, and this is what we want our script to accomplish. So we're going to save our script. So Control O to save, and then Control X to exit. Check that we're still executable. There's no reason why we wouldn't be, but it's nice to check. So my file's still green. It's still listed as being as executable. It's got slightly larger again, which is nice. And then we're going to remove our muscle input file because we don't want to double the size of it. We don't want to double our input file, and we don't want to give 24 sequences to muscle. We just want to give one sequence to muscle. Actually, the other thing that I'm going to do, and this is going to seem slightly superfluous, I'm just going to go back into my script. Sorry, I forgot that I was going to do this. Get uniprot data is at the top of my script. At the very top, I am going to run Conda activate MSA. Okay, and the reason for doing that is because I want to ensure that whenever I run this script, whatever Conda environment I run it from, it's going to work. And if I run it from my base environment, then muscle isn't installed in my base environment, so it's going to get down to muscle and it's going to fail. Whereas if I activate the multiple sequence of the MSA environment at the beginning of the script, regardless of whether I've already activated that environment or not, this script will run and will work. So it doesn't matter what environment I'm in when I start the script. Adding the Conda activate in at the top will make sure that I run this in the correct environment. So activate the right Conda environment. So again, save and exit. Incidentally, I should say that my erstwhile colleague Peter, who will be familiar to many of you from the live comments, made a very good suggestion yesterday, which is that I should make my versions of these scripts available so that you can download them after the session if you want to, and I will absolutely do that, and I will let you know tomorrow where I've started to put these scripts. I'll put them in a web accessible location for you so that you can find them and download them, so that they're all my versions of them are available, and yeah, that was a good suggestion of Peter's that he made yesterday. I might make a repository on GitHub, because we might come to GitHub in a future lesson, so I might make a repository on GitHub and put them in there. Right, okay, so that's my script. So my script is done and written and ready. We can look at the contents of it with cat, just to make sure that it says all of the things that we want it to say, and so that it can sit on the screen for a couple of minutes for you, so that if you're running slightly behind, which I know some of you might be, you can have a look at what my script looks like before we run it. I'm going to activate the correct Conda environment at the beginning of the script to make sure that we've got our software available to us within the script. Then we use cat with command substitution, this dollars round brackets notation, to get our Uniprot identifiers. That's our input for our for loop. We set another variable to be the stub URL for the Uniprot API. And then in our for loop, we download all of those sequences. So we download each of those 12 sequences from Uniprot using wget. Then we cat them into a single input file for FastA using standard output redirection to append to this muscle input file. And we remove the original FastA files that we've downloaded just to tidy up behind us. And then finally, on the very last line of the script, we actually run the multiple sequence alignment. So we run muscle to construct our multiple sequence alignment. Okay, so now we're going to run this script. So it's executable, and we're going to do get Uniprot data and run the script. So this will download our 12 Uniprot entries, concatenate them into a single file, and then construct a multiple sequence alignment from that input. Okay, here we go, everybody. So it's downloading the data, which we've seen a few times now, so we know that that was good. We knew that that would work. It's downloaded the data, and there you go. That very quick thing that happened at the end, that happened in just under a second or just over a second, was the multiple sequence alignment being built. So that's the standard output. That's actually standard error from muscle. So that's muscle's kind of logging output when it runs. So it does a bunch of iterations, builds an alignment, refines the alignment, and produces it on the disk. So, okay, all of that data got downloaded, all got put into a single input file, and then the alignment ran and created an output file. And we can see from the files in our present working directory now, we have our input file, muscle input.fasta. We know that that's going to look right because we've already checked that. And then we get muscle output.clw. And if we look at that file, that is the output of our multiple sequence alignment. And in less, you'll see the cluster format is relatively human readable. So we get the alignment, I think it's 60 characters at a time. And you can see that we have managed to build a multiple sequence alignment. That top sequence, the one which I think might be a mistranscribed ID, you can see really isn't aligning very well at all to the rest. Whereas all of the others seem to align okay to each other. There is one other outlier a little bit. This G1 is a little bit different. This one here, which is Danari, so that's Danio Ririo, so that's zebrafish. So that's also a little bit different, which I guess was what you would expect when you look at the others being rat, mouse, this is cat, I think this is the macaque. You've got human, you've got the gorilla. So you've got a whole bunch of apes and kind of mammals and vertebrates. And then you've got the zebrafish. You would kind of expect the zebrafish to be a little bit of an outlier. So you can see the vertebrate ones are all very similar to one another. There's really not much difference between those in this alignment at all. Whereas the zebrafish one and the one below it, which actually looks like it might be from an anaconda, I guess. And so that one is also quite different. I didn't deliberately get the anaconda sequence, but it's weirdly apt for what we've been doing the last couple of days. So this is our multiple sequence alignment. And tomorrow, what we will do is we will use a tool that's not a command line tool. We'll use a different tool for actually looking at and working with a little bit this multiple sequence alignment. Just so I want to show you some actual bioinformatics. So we're going to use JalView to take a look at this multiple sequence alignment and have a bit of a play with it. But between now and then, I am going to check that top sequence and see if I've got it right, if it actually is just a distant ace relative, or if it's really not an ace and it's throwing off our multiple sequence alignment more than perhaps it should. See, there are little regions where it's similar, like this pair of leucines here, slightly similar, but it's not really very convincing as an alignment. So I'll have a check. I'll look into it and I'll see. Okay, so we have got to the point where we've written really quite a complicated script now to do some like really genuinely proper bioinformatics. This is exactly the kind of script that I may well write from time to time to download some data and generate multiple sequence alignment from it. So we've done some real bioinformatics work, which is great. We're only just over 2 weeks in, if you think about it. Doing an hour a day, I think we've done really, really well to get this far and to produce this kind of script in that short time. I hope that if you are keeping up, that you've got a real sense of achievement, because I think you should. So tomorrow we'll take a look in a bit more detail at that alignment, and we'll have a bit of a play with JalView and with the alignment itself, and have a bit of a muck about. I won't necessarily have been finishing off digging a pond all day tomorrow, so I won't be quite as discombobulated and sort of disconnected from my work as perhaps I have been today. And I apologise if I've been a little bit distracted today, but that's the nature of, even when you're trapped in your house, that's the nature of having days off. So I hope that everybody is keeping themselves well and safe and sane and managing to get some fresh air, even if you've not necessarily got your own outdoor space, getting out for a walk and so forth, and keep yourselves safe and well. And I will see you all tomorrow for some more bioinformatics. So thanks everybody for tuning in, and see you anon. Goodbye.